Hello, this is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this video, we are going to define the simple pendulum, give the expression of the mechanical energy of the simple pendulum-Earth system, determine the differential equation that governs the motion of the undamped simple pendulum, introduce the solution of the differential equation and give the expressions of omega 0 and t0, verify that t0 is independent of m, and verify that t0 is proportional to L squared.
This is a pendulum. It consists of an object attached to a light inextensible cord. Now, if the dimensions of the object are neglected relative to the length of the cord, then this object can be considered as a particle, and this pendulum is considered as a simple pendulum. Now, our pendulum is in its equilibrium position. Let's start the oscillations of the pendulum. I will displace the pendulum from its equilibrium position and then I will release it from rest. As you see, the pendulum oscillates in the vertical plane about a horizontal axis passing through the upper end of the cord.
This figure shows the pendulum in a certain position during its oscillation. In this position, the pendulum makes an angle of theta with the vertical. The vertical position is the equilibrium position of the pendulum. Here we have the pivot, and here we have the horizontal axis of rotation. Now, let's move to the expression of the moment of inertia of the particle about the axis of rotation. As you know, the moment of inertia of a particle is given by multiplying the mass of the particle by the square of the distance separating this particle from the axis of rotation. So we have I is equal to ml squared. I is the moment of inertia about the axis, m is the mass of the object or the particle, and L is the distance between the axis and the particle. Recall that the mass is expressed in kilograms in the SI units, and L in meters, and I in kilograms meters squared. Now, let's move to the expression of the mechanical energy of the pendulum-Earth system. You know that ME is equal to KE plus GPE. Now, what is the kinetic energy of the particle P? The kinetic energy is 1/2 I theta prime squared. But remember, because P is a particle, so 1/2 I theta prime squared can be replaced by 1/2 mv squared. They are the same. Now let's move to the gravitational potential energy. As you know, it is equal to mgz. But what is z? Z is the altitude measured relative to the reference level. So relative to this reference level, we have this z. So z, as you see, it is the altitude relative to the reference level. Now we need to calculate z. Consider the right-angled triangle OAP. Cosine theta is equal to the adjacent OA over the hypotenuse L. So OA is equal to L cosine theta. But what is the relation between OA and Z? Actually, Z is negative because the particle is below the reference level. So Z is equal to minus OA, which is equal to minus L cosine theta. Now, GPE changes according to the chosen reference level. For more information, watch the video whose title is Simple Pendulum dash solve the problem. Now we have ME is equal to 1/2. We replace I in the above expression by ml squared, and we replace Z by minus L cosine theta, and this is the expression of the mechanical energy.
Differential equation of free undamped oscillations. Since friction is neglected, or the sum of the works done by the non-conservative forces is equal to zero, then the mechanical energy of the system is conserved. But in our problem, the expression of the mechanical energy is equal to 1/2 ml squared theta prime squared minus mgl cosine theta, proved in the previous slide. Recall that if y is a function of time and is equal to cosine u, and u is also a function of time, then the derivative of y with respect to time is equal to minus u prime sine u. Now differentiate both sides with respect to time. The derivative of the mechanical energy with respect to time is equal to 0 since it is constant. Half ml squared is constant, and the derivative of theta prime squared is equal to 2 theta prime theta double prime. mgl is constant, and the derivative of cosine theta is equal to minus theta prime sine theta. 2 times half becomes 1, minus times minus becomes 1. Therefore, 0 equal ml squared theta prime theta double prime plus mgl theta prime sine theta. But in case of small angles, sine theta is approximately theta in radius. So rearrange by taking theta prime as a common factor, then theta prime equal ml squared theta double prime plus mgl theta is equal to 0. Here we have two solutions. Theta prime is equal to 0, or ml squared theta double prime plus mgl theta is equal to 0. But physically, theta prime is equal to 0 is rejected or cannot be equal 0 as a solution. So the solution is ml squared theta double prime plus mgl theta is equal to 0. Divide both sides by ml squared. So theta double prime plus g over l theta is equal to 0, which is the second order differential equation that governs the variation of theta.
After determining the differential equation using the principle of conservation of mechanical energy, we're going to determine this equation using Newton's second law for rotation. Now, this law is called in French references as the theorem of angular momentum. So our system is the pendulum, and then what are the external forces acting on the pendulum? So we have the support reaction R at the axis delta. We draw the pendulum in a certain position during its oscillation, and in this position, R is shown on the figure. Now, the second force is the weight of the particle. Let's move to Newton's second law for rotation. The sum of the external moments acting on the system is equal to the time derivative of the angular momentum sigma. But because the moment of inertia of the system of the particle about the axis of rotation delta is equal to ml squared, which is constant, then d sigma by dt becomes I theta double prime. So this is going to be moment of R plus moment of mg is equal to I theta double prime. Now, we need to determine the expressions of the moment of R and the moment of mg. Let's start with R. So as you see in the figure, R intersects the axis of rotation, and so its moment about this axis is 0. Let's move to mg. But first, in general, when you want to determine the moment of a force about a fixed axis of rotation, you can use this expression, plus minus Fr sine theta, where F is the magnitude of the force and R is the distance between the point of application of the force and the axis of rotation, and theta is the angle between F and R. Now, we have a plus or minus depending on whether the force tends to rotate the system in the chosen positive sense or opposite to the chosen positive sense. So let's move to our example. We want to determine the expression of the moment of the weight about this axis of rotation. First, let's discuss the minus sign. In the figure, we choose the counterclockwise as the positive sense. And in this position, the weight mg tends to rotate the pendulum clockwise in order to return the pendulum to its equilibrium position. So we have the minus sign. Now our force, the magnitude of our force is mg, and the distance r between the axis of rotation and the point of application of the force is equal to L. So r is equal to L, as you see. And the angle between mg and r is this angle. But because mg is parallel to the distance OA, so this angle and this angle are corresponding. So this angle is equal to theta. So we have minus mg L sine theta. Now for small angles in radians, sine theta is approximately equal to theta in radians, and this is going to be moment of mg is equal to minus mgl theta. Now replace moment of r and moment of mg by their expressions in this equation. So this is going to be 0 minus mgl theta is equal to I theta w prime. Now replace I by ml squared and rearrange. This is going to be mgl theta plus ml squared theta w prime is equal to 0. Divide the equation by nl squared. This is going to be theta w prime plus g over l theta is equal to 0. This is the second order differential equation that governs the undamped oscillations of the simple pendulum. Now, let's move to the nature of the motion of the pendulum. So we have the differential equation theta w prime plus g over L times theta is equal to 0. This differential equation is of the form theta w prime plus omega 0 squared theta equal 0, with omega 0 squared equal g over L being a positive constant. So the nature of the motion of the simple pendulum is simple harmonic motion, or SHM. Now let's move to the time equation, or the solution of the differential equation. So the solution could be a sine omega 0 t plus phi, or a cosine omega 0 t plus phi. Now, what is A? The absolute value of A is equal to the amplitude of oscillation theta m. Recall that the amplitude is a positive quantity. Now, you know that sine omega 0 t plus phi varies between -1 and +1, which means that theta varies between minus theta m and plus theta m. Now, this means that the pendulum oscillates between minus theta m and theta m. Finally, what do we call the angle omega 0 t plus phi? Omega 0 t plus phi is the phase at an instant t. And because omega 0 t plus phi is an angle, so its SI unit is the radian.
Focus, please. This is important.
Now, expressions of the properties of the oscillations. In the previous slide, we proved that omega 0 squared is equal to g over L. So, the natural angular frequency omega 0 is equal to the square root of g over L. Omega 0 is always positive, and the SI unit of omega 0 is radians per second. Let's move to the natural period. The natural period T0 is given by this formula. T0 is equal to 2 pi over omega 0. Replace omega 0 by the square root of g over L. So we get a relation between T0, L, and g. So that T0 is equal to 2 pi the square root of L over g. Now, the natural frequency. The natural frequency is given by this formula. F0 is equal to 1 over T0. Replace T0 by 2 pi over omega 0. We get a new relation between F0 and omega 0, so that F0 is equal to omega 0 over 2 pi. If you are interested in the physical meanings of omega 0, F0, the phase angle, and the initial phase angle, watch the video whose title is Time Equation of Motion of a Horizontal Elastic Pendulum.
Let's verify the formula formula that gives you the natural period of the simple pendulum. So we have T0 is equal to 2 pi times the square root of L over G. Let's take G as 9.8 meter per second square. Now I will measure the length of the chord. So this is the length of the chord. It is 40 centimeters. So 0.4, Kinda please the answer, over 9.8 and the answer is 1.27 seconds. Now let's verify this value experimentally. But first, this mathematical relation gives you the natural period of the simple pendulum for small angles, and in this case friction is neglected. We will measure the time for 10 complete oscillations, and then we will divide the time by 10 to diminish the experimental error. And friction can be neglected during the first 10 oscillations. So Kinda, are you ready?
Yes.
I will displace the pendulum by about 10 degrees, a small angle, okay? And then I will release it from rest. Ready?
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the answer is. So as I said, we can neglect the friction during the first 10 oscillations, so this measured value of the period can be considered as the natural period of the pendulum. And this time is, Kinda?
12.75 seconds.
Perfect. So T0 is equal to 12.75 divided by 10, and the answer is 1.275 seconds. And the values are very close, so the natural period of the simple pendulum is verified.
The expression of the natural period T0, which is equal to 2 pi, the square root of L over G, says that the natural period of the simple pendulum is independent of the mass m of the particle, since we have no mass in this formula, and it is directly proportional to the square root of the length of the string, since the square root of the length L of the string is in the numerator. So T0 squared is proportional to L. Also, the natural period of the simple pendulum is inversely proportional to the square root of the gravitational acceleration in the place of the experiment, as you see, since the square root of G is in the numerator. Therefore, T0 squared is inversely proportional to G. In the next slide, Madame Jeanette and her student will verify that experimentally T0 is independent of the mass m and directly proportional to the square root of the length of the string.
In the previous experiment, we determined the natural period of our pendulum, and the value was 1.27 seconds. Now look at the formula. The natural period is independent of the suspended mass, which means that if we change the suspended object by another one having a different mass, the natural period must be or must remain the same. So we will follow the same procedure as in the previous experiment. We will shift the pendulum from its equilibrium position by a small angle, and then we will release it from rest. This is 10 degrees. We will measure the time for 10 complete oscillations and then divide by this time by 10. Eileen, are you ready?
Ready.
1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Deal? So, what is delta T?
12.45.
12.45 seconds. So, T0 is equal to delta T over 10, which is equal to 12.45 over 10, and the answer is 1.245 seconds. As you see, the values are very close, so really T0 is independent of the suspended mass. Now, consider the formula. T0 is equal to 2 pi times the square root of L over the square root of G. 2 pi over the square root of G is constant, which means that T0 is directly proportional to the square root of L. Square both sides. T0 squared is equal to 4 pi squared over G times L. Again, 4 pi squared over G is constant, so T0 squared is directly proportional to L. So we must verify this result experimentally. Now, the length of our chord is 40 centimeters, and with this length we have this natural period. Now, I will replace the chord by another one having half the initial length. So, the square of the new period must be half the square of the initial period. Lynn, give me the square of the initial period.
It's 1.61.
Okay, so it is
Seconds
1.61 seconds squared. Now, the square of the new period must be half the initial value. So, divide the answer by 2, please.
It's 0.805.
Okay. So, you need to get this value experimentally. Now, this is our pendulum. Now, this new pendulum has a length of, as you see, it is 10 centimeters. Okay. Now, again, it's 20 centimeters. Again, I will displace the pendulum by a small angle from its equilibrium position. We measure the time for 10 oscillations. So 10 degrees is like this. Are you ready, Lian?
Yeah.
So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
It's 9.44.
So the new period is,
9.
so it is 9.24, sorry, this is the time for, over 10. So it is 9.24 over 10 seconds, which is equal to 0.924 seconds. Now, please give me, take the square of this value, so 20 prime squared,
0.853.
second squared. Now, look at the calculated value and the experimental value. They are very close, and so this result is verified. The square of the natural period is proportional to L.
Remark: the simple pendulum is a special case of the physical or the compound pendulum. Observe these two pendulums. The distance between O and the center of mass G of a compound pendulum is denoted by A. This distance in a simple pendulum is always equal to the length of the string, since the center of mass of the simple pendulum coincides with the position of the particle. So, OG, which is equal to A, is always equal to L in a simple pendulum. And the moment of inertia of the particle in the simple pendulum about the axis of rotation delta is always equal ml squared. Now, referring to the differential equation that governs the motion of the compound pendulum, theta double prime plus mga over I theta is equal to 0, replace A by L and replace I by ml squared, we get the differential equation, which is theta double prime plus mgl over ml squared theta equal to 0. So we get the differential equation that governs the motion of the simple pendulum, which is theta double prime plus g over l theta is equal to 0. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.